Okay, let's talk about something that literally affects every single one of us, even if you live thousands of miles away from the nearest ocean. Today, we are diving into the absolute domino effect that is El Nino, and we're going to transform how you think about this. It's not just some periodic weather event you catch on the evening news. It's actually a massive global macroeconomic and ecological shockwave that literally shapes human history. To really wrap our heads around this, we've got a pretty clear roadmap today. First, the engine of chaos. Second, global shockwaves. Third, the macroeconomic earthquake. Fourth, the Indonesian paradox. And finally, engineering resilience. Starting right off with section 1, the engine of chaos. So our journey starts way out in the equatorial Pacific, which is basically a giant thermodynamic engine. Imagine tilting a massive bathtub filled with water. In a normal neutral state, you've got these strong trade winds blowing from the Americas toward Asia. They act like a huge broom sweeping all the warm surface water to the western Pacific. This actually tilts the ocean itself. The sea level in the west gets pushed about 40 to 50 centimeters higher. And because all that water gets pushed west, it pulls deep, cold, nutrient-rich water up to the surface in the east, which is a process we call upwelling. But during El Nino, those trade winds just weaken, or they even reverse into westerly wind bursts. When that happens, gravity takes over. That huge pile of warm water sloshes right back to the east via these massive underwater ripples called Kelvin waves. And this pushes the boundary between the warm and cold water, the thermocline, way deep down, completely shutting off the eastern Pacific's cold water upwelling. Now you might be wondering, why doesn't it just fix itself? Well, it all comes down to a self-amplifying loop discovered back in 1969 called the Bjerknes feedback. Basically, as that warm water travels east, it heats the eastern Pacific surface, flattening the temperature difference between the east and the west. But here's the catch. That temperature difference is exactly what drives the trade winds in the first place. So the winds weaken even more, which lets more warm water flow east, causing more warming, which further kills the winds. They just keep feeding each other until this massive global climate shift is completely locked in. Which brings us to section 2, global shock waves. Once that engine revs up, that localized ocean warming violently disrupts our whole global ecology. But modern science actually shows us that El Nino isn't just one single thing. Every event is unique, and we basically have two main flavors. First, there's the Eastern Pacific or your classic El Nino, where intense warming hugs the South American coast. But lately, we are seeing a lot more of the Central Pacific El Nino, often called Modoki, which is a Japanese term for similar but different. In a Modoki event, the maximum warming is isolated right in the middle of the Pacific, leaving the east and west colder. And this totally alters how the atmosphere responds. Take Indonesia's Sulawesi Island, for example. A Modoki El Nino causes mild rainfall deficits there, but a classic Eastern Pacific El Nino that triggers absolutely devastating droughts. By distorting the atmosphere above the ocean, El Nino basically acts as a master weather maker for the entire planet. I mean, it literally splits the North American jet stream, giving Canada these warm, dry winters while dumping extreme rain on the southern US and normally dry southern California. In South America, coastal deserts in Peru and Ecuador get battered by decades worth of rain in just months, just destroying infrastructure. Meanwhile, on the complete other side of the world, the atmospheric system sinks, creating a total cap on rain clouds. This causes monsoons to fail, extreme drought in India and Southeast Asia, and massive catastrophic bushfires in Australia. It even shifts global storm patterns, amplifying deadly typhoons in the Pacific while surprisingly suppressing hurricane formation in the Atlantic. But the shock waves aren't just in the sky, right? Without that cold and nutrient-rich upwelling in the eastern Pacific we talked about, the ocean surface rapidly mutates into this sterile, sun-baked wasteland. Without deep-sea nitrates and iron, the microscopic phytoplankton can't survive. And when the very base of the food web dies, it triggers a horrific biological collapse. Massive schools of anchoveta of Peru and Chile suffer a total biomass collapse, and that starvation cascades all the way up, hitting millions of seabirds, sea lions and seals. Not to mention, this abnormally warm water triggers devastating mass coral bleaching events all across the Indo-Pacific. Let's move into part 3, the macroeconomic earthquake. If you're thinking this just means a bad season for fishermen, think again. Get a load of this number, $5.7 trillion. The 1997/1998 Super El Niño didn't just cause bad weather. It incinerated a staggering $5.7 trillion in global GDP. The 2015/2016 event wasn't far behind, burning up almost $4 trillion. And these aren't just quick, temporary blips. Studies prove a persistent hysteresis effect, meaning the economic scar of lost production lasts for 3 to 5 consecutive years, even after the weather returns to normal. How does it do so much damage? It basically cripples the 3 fundamental pillars of global economic output simultaneously. First, it sabotages technical productivity. Hydropower dams run dry, causing blackouts and massive storms disrupt maritime ports. Second, it destroys physical capital. Flash floods wash away railroads, agricultural irrigation systems, and totally flood mining operations. Third, it slashes labor output. Extreme weather displaces entire populations and causes huge spikes in tropical diseases like malaria and dengue fever that just thrive in stagnant floodwaters, directly reducing human labor hours. The real takeaway here is that El Niño systematically attacks our most vulnerable agricultural and mining sectors, creating a massive global supply shock. Take cocoa, for example. Simultaneous droughts in West Africa and Asia during a recent El Niño spiked daily futures prices by an incredible 250%. For Robusta coffee in Vietnam and Indonesia, the dry heat literally ruins the flowering process. In Malaysia and Indonesia, a lack of rain stops palm oil fruit bunches from even forming. And mining? It's a double-edged sword. Droughts halt the hydropower needed for smelting nickel in Indonesia, while extreme floods wash out mountain logistics for copper in Chile. Over in Australia, heat waves and bushfires severely degrade export quality wheat. So naturally, all these agricultural failures lead to massive spikes in international food prices, and this creates a totally vicious cycle for developing nations. Governments are forced to spend their precious foreign reserves on emergency basic food imports. That drains their accounts and crashes the local currency's value against the US dollar. So now the central bank is trapped in a total nightmare dilemma. Do they increase fiscal subsidies and create runaway debt? Or do they aggressively hike interest rates to stop inflation, which destroys domestic credit and traps their citizens in prolonged stagflation? It's a brutal catch-22. Next up, Section 4. The Indonesian Paradox. When we zoom in on the Indonesian archipelago, this climate engine creates one of the most fascinating yet frustrating ecological contradictions on Earth. It's a stark contrast between devastating disasters on land and an absolute miracle of marine abundance in the ocean. On land, the lack of rainfall causes a total agrarian collapse. Rice paddies fail and massive organic peatlands dry out, igniting into these mega fires that choke the entire region in toxic smog. But offshore? Totally different story. When El Niño interacts with the positive phase of the Indian Ocean Dipole, which is a regional climate driver, it supercharges coastal winds. This drives massive upwelling along the southern coast of Java, bringing ancient nutrient-rich deep water to the surface. That triggers an explosion of microscopic chlorophyll and phytoplankton, resulting in a staggering historic boom in fish populations like sardines and squid. But here is the heartbreaking catch. Without the proper infrastructure to freeze and store this biological bonanza, it turns into a total logistical nightmare. The commercial cold storage facilities just don't exist at the scale needed. So this unprecedented harvest of fresh fish literally rots on the docks, and the massive oversupply instantly crashes market prices, meaning this theoretical economic boom actually harms the welfare of the local fishermen who worked so hard to catch it. Finally, we've reached Section 5, Engineering Resilience. So facing all of this chaos, how do we fight back against a trillion-dollar thermodynamic engine? Well, we have to shift from reactive firefighting to proactive defense. And our very first line of defense is prediction. We can't stop El Niño, but we can absolutely see it coming. Global meteorological agencies use this massive network of deep-sea sensors called the TO/Triton array, anchored right across the Pacific equator. Combine that with precision satellites tracking those westerly wind bursts, and we can monitor the buildup of warm water volume in real time. All this data feeds into supercomputers, allowing agencies like Indonesia's BMKG to issue deterministic early warnings with a crucial 3 to 8 month lead time. They can literally map out the vulnerability zones well before the first drop of rain is even missed. Armed with that early warning, nations can take some brilliantly structured action. Indonesia's Ministry of Agriculture, for instance, rolls out a 5-pillar strategy to secure food sovereignty. First, geospatial mapping tells them exactly which rice paddies will go completely dry and which ones they can still save. Second, they deploy pampanization, which is this aggressive rollout of tens of thousands of water pumps and small reservoirs called embung to force water into drying fields. Third, they distribute genetically engineered drought-resistant seeds that can be harvested much faster. Fourth, they rush mechanized harvesters to the fields to basically beat the evaporation clock. And fifth, strict interagency synergy is enforced on the ground to make sure communities don't end up fighting over the remaining water rations. But it goes beyond logistics. They are literally engineering the atmosphere. Using weather modification technology, military aircraft are deployed to intercept clouds before they vanish. They seed these cumulus clouds with hygroscopic salt, creating artificial condensation nuclei. This effectively squeezes the remaining moisture right out of the sky, forcing targeted rain over vital drinking water reservoirs to keep them topped up, and strategically soaking those vulnerable peatland domes in the jungle to prevent those massive smoke-producing wildfires before a single spark can even catch. Ultimately, we have to look to the future. Our modern scientific monitoring and these aggressive agricultural mitigations, they are incredible achievements. However, the data confirms a pretty terrifying trend. As greenhouse gases accelerate global warming, the intervals between these massive super El Niños are shrinking. What used to be a once-in-a-generation shock is becoming incredibly frequent. So we have to ask ourselves, are these adaptive strategies enough to secure our global economic and ecological survival in the coming decades? Or are we just bailing water out of a sinking ship? Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I will catch you on the next one.